Electric force. The electric force is one of the most powerful fundamental force in the universe. This is the force that exists between all charged particles. The direction of the force vectors depends on the signs of the charges. If the particles have the same sign of charge, they repel each other. If instead the particles have opposite signs of charge, they attract each other. The equation for the electrostatic force acting on the particle is called Coulomb law. Coulomb's law, a law stating that like charges repel and opposite charges attract with a force proportional to the product of charges and inversely proportional to the square of distance between them. Figure 1. In Figure 1, where particle 1 has charge q1 and particle q has charge q2, the electrostatic force between two charges is given as F is equal to K Q1 Q2 over R2. This is Coulomb law, where R is the separation between the particles and K is a positive constant called the electrostatic constant or the Coulomb constant. R is the unit vector having magnitude 1 and K is equal to 1 over 4 pi epsilon naught, where the value is given. The quantity E naught, called the permittivity constant, sometimes appears separately in equation and is E naught. The value is given. So Coulomb law can be written as F is equal to 1 over 4 pi epsilon naught Q1 Q2 over R2. Conservation of charge. The law of conservation of charge states that electric charge can neither be created or nor be destroyed. An example of charge of conservation occurs when an electron and its antiparticle, the positron, undergo an annihilation process transforming into gamma rays high energy light. In applying the conservation of charge particle, we must edit the charges algebraically with due regard for these signs. In the annihilation process, the net charge of the system is zero both before and after the event. Charge is conserved. In pair production, the converse of annihilation charge is also conserved. In this process, a gamma ray transforms into an electron and a positron. The electric field due to a point charge. To find the electric field due to point charge, we place a positive test charge at a point near the particle distance r. From Coulomb's law, the force on the test charge due to particle with charge q is given. The direction of force is directly away from the particle if q is positive because q naught is positive, and directly toward it if q is negative. We can write the electric field set up by the particle at the location of test charge. We can find the magnitude at any given distance r by converting to a magnitude form. In general, if several electric fields are set up at a given point by several charged particles, we can find the net field by placing a positive test particle at a point and then writing out the force acting on it due to each particle, such as F01 due to particle 1. Forces obey the principle of superposition, so we just add the forces as vectors. To change over to electric fields, so this is the topic. Hope you all will like the video.